Outstanding diversity now beckons with new fascination. Despite its obviously empty appearance, Titan seems to harbor life forms unlike anything we've ever seen. What new discoveries has the scientific community made on Titan? What lies under the surface of Titan's murky lakes, and what mysteries do its frozen landscapes conceal? Does Titan harbor life forms like our own Earth? Join us as we explore how NASA finally discovered life on Titan, the amazing new discoveries on Saturn's moon Titan. Titan is Saturn's biggest moon and the second largest in the solar system, surpassing all of the solar system's dwarf planets. It is the only moon known to have a thick atmosphere, as well as the only known object in space, other than Earth, with clear evidence of stable surface liquid bodies. Titan is one of Saturn's 7 gravitationally spherical moons, and it is the second most distant of them all. Titan, commonly referred to as a planet-like moon, is 50% bigger in diameter than Earth's moon and 80% more massive. It is the second largest moon in the solar system after Jupiter's moon Ganymede. Titan is bigger than Mercury but only 40% as massive, primarily composed of less dense ice. Discovered in 1655 by Dutch astronomer Christian Huygens, Titan was Saturn's first known moon and the 6th known planetary satellite. Titan orbits Saturn at 20 Saturn radii. Saturn subtains an arc of 5.09 d from Titan's surface, and if visible through the moon's dense atmosphere, it would look 0.4 times bigger in diameter in the sky than the moon from Earth, which subtends a 0.48 DE arc. For a long time, the moon, roughly twice the size of Earth's moon, was regarded as the most viable prospect for alien life in the solar system. The Huygens Atmospheric Structure Instrument, HASI, conducted the first in-situ observations of Titan's atmosphere. HASI measured atmosphere temperature, pressure, and density from a high of 1,400 kilometers to the surface. Long before ESA's Huygens mission landed on Titan, scientists knew that the moon's thick atmosphere was primarily made of nitrogen with some methane. However, the structure of the atmosphere, including temperature and pressure at various altitudes, was poorly understood. The HASI equipment directly assessed the density of the upper atmosphere by measuring the probe's deceleration rate as it descended into the atmosphere. The temperature was calculated using predictions of how it should fluctuate with density and height. HASI directly recorded pressure and temperature in the lower atmosphere below 160 kilometers and on Titan's surface, as well as electrical parameters, including permittivity and ion distribution. The data revealed that the upper atmosphere, the thermosphere, was usually warmer and denser than predicted. Titan's atmosphere was likewise discovered to be extremely stratified. Above 500 kilometers, the average temperature was around -100 degrees Celsius, although major variations of 10 to 20 degrees Celsius were seen because of inversion layers and other phenomena like gravity waves and tides. Contrary to theoretical projections, the mesosphere was almost entirely missing. Temperatures increased fast below 5,100 kilometers, peaking at -87 degrees Celsius at the top of the stratosphere at 250 kilometers altitude. The temperature then progressively fell throughout the stratosphere, reaching a minimum of -23 degrees Celsius at 44 kilometers. This indicated the border between the stratosphere and the troposphere. The temperature increased again as the probe approached the surface, reaching a frigid -10 degrees Celsius at the landing spot. The surface pressure was 1.47 times higher than on Earth. Many other instruments, including the Hubble Space Telescope and the Cassini Orbiter instruments, Composite Infrared Spectrometer, CIRS, Ultraviolet Imaging Spectrograph, UVIS, Visible and Infrared Mapping Spectrometer, VIMS, were used to measure Titan's atmosphere. This measurement detected evidence of gases that imply organic substances. After the Cassini-Huygens mission, it was discovered that many of Titan's lakes are most likely made up of liquid methane rather than water, which was initially disappointing. But the ongoing mystery of whether life could exist on Titan continued like a cosmic puzzle waiting to be solved. Saturn's moon Titan is a fascinating world that, from a distance, resembles the greenish-brown counterpart of Earth. In fact, Titan and Earth are the only celestial worlds identified in the solar system with stable, cloud-rich atmospheres. Scientists have been able to study Titan more clearly in recent decades due to advances in telescope technology. Among other things, they identified formations indicating the presence of seas and lakes. These findings, along with the planet's greenish hue and the fact that it possesses an atmosphere, solidified Titan's status as the most promising contender for the discovery of alien life. The Cassini-Huygens mission, with its twin spacecraft launched in October 1997, researched Saturn for about 30 years. While Huygens' lifespan was estimated to be much shorter, Huygens had one purpose from the start: to fly through Titan's atmosphere and land on its surface. On December 25, 2005, the moment came. Huygens was separated from Cassini, and 2 weeks later, the lander descended into Titan's atmosphere, hanging on a parachute. Huygens spent 2 hours and 28 minutes collecting data in the atmosphere before landing on the surface and collecting data for an additional 56 minutes. Since those momentous hours, we on Earth have learned a lot more about Titan's real nature, but the mission is yet to answer all the puzzles surrounding this intriguing moon. Titan's atmosphere is rich in nitrogen, similar to ours on Earth, with significant levels of methane, hydrocarbons, and evidence of organic molecules. Titan has a nitrogen concentration of 98.4%, with no oxygen in its atmosphere. Methane exists in the higher layers of the atmosphere due to its low density. Interestingly, various organic molecules such as ethane, propane, ethene, and hydrogen cyanide were discovered. Huygens could also identify traces of helium, carbon dioxide, and water. Although nitrogen plays an important part in the terrestrial processes that allow organic life to exist, the atmospheres of Titan and our Earth differ substantially since Titan has no oxygen. Since the mission began, planetary scientists have used the Cassini spacecraft's radar system and visible and infrared mapping spectrometer, VIMS, to analyze the composition of the region Huygens sailed across. Before Huygens, Titan's surface was a complete mystery. It was obscured by a dense cloud. As the probe penetrated the layer of haze within the atmosphere, Huygens revealed a previously invisible world. According to Jean-Pierre Lebreton, ESA's Huygens project scientist, Lawrence Soderblom of the United States Geological Survey has been trying to make sense of what Huygens saw. Discovering the Huygens landing location in Cassini photos proved to be one of the most challenging issues. When we looked at the ESA, synthetic aperture radar, images and compared them to the VIMS data, we saw little correlation, Lawrence Soderblom said. The radar scans did not indicate the boundary between the amazing highlands and dark lowlands that Huygens traveled over. Finally, a clue appeared in the form of 2 solitary black sand dunes around 30 kilometers north of the landing location, visible in both ESA and Huygens photos. They are most likely made up of sugar-sized hydrocarbon grains of between 100 and 300 microns in diameter. Most of Titan's dunes are massive, up to 100 kilometers over the Black Plains and separated by 10 miles. More significantly, 2 dunes visible in both radar and optical photos provided the scientists with the information they needed to begin their study. We started to piece together a model of the way we think the surface behaves, Soderblom said. In this theory, the region surrounding the Huygens landing site is a vast plain of filthy water ice covered by blankets of organic carbon-bearing deposits that form the brilliant highlands and dark dunes. The brilliant layers are undetectable to radar wavelengths, therefore, Cassini SAR photos can look through to the bottom filthy water ice layer, which is rough in some places and smooth in others. The deposits develop when sun UV light and charged particles react with Titan's plentiful methane at high altitudes, producing carbon and hydrogen-bearing hydrocarbon molecules like ethane and acetylene, as well as more complex nitrogen-bearing compounds known as tholins. These products fall down to the surface as aerosols, similar to how smog particles develop and cover Earth's surfaces. However, on Titan, these deposits can accumulate to depths of hundreds of meters. The dunes are made up of sand-sized debris that gathered during its descent or was reworked by geological processes on the surface. The ice and biological landscapes are as unique as they are magnificent. To the north of Huygens' landing site are the brilliant highlands, which have channels that split 4 or 5 times as they climb into the hills. Stereoscopic photos from Huygens Descent Imager Spectral Radiometer (DISR) camera have now been examined, revealing that some of the ridges between the channels reach heights of 150 to 200 meters and have slopes of 30 degrees. This is extremely rugged terrain, explains Soderblom. The design implies that these are drainage canals with liquid methane pouring as rain. Close by are stubby canyons with few branches. They were most likely generated by spring sapping, a process in which methane travels through the subsurface before appearing as a spring near the base of a hill. The spring erodes the hillside, forcing it to fall and create a cliff face. The third section is a flat black plain. This is primarily water ice combined with lowland grit. Titan's river channels, canyons, and floodplains rival the variety seen on Earth, Soderblom said. The dark plains reveal signs indicating that the region occasionally receives flash floods, although not from the highland drainage canals. Instead, vast amounts of liquid methane appear to flow east-west. Planetary scientists may now begin to reconstruct the chain of events that resulted in the development of this unique terrain. Huygens and Cassini have taken giant steps forward in our understanding of Titan, Soderblom said. Huygens was the first probe to land on a moon other than Earth's moon. NASA and other space agencies initially showed little interest in Saturn and Jupiter's moons. International interest only grew after it was discovered that Titan mimics Earth in such an unusual way. Since then, probes and telescopes have discovered countless additional moons orbiting the gas giants, each with its own distinct surface conditions, volcanism, and water traces. Unlike the gas giants, which are hardly made up of solid components, these planets' moons are rocky worlds similar to Earth. When Huygens landed on Titan, it discovered a reddish-harsh environment of rocks and cliffs, as well as indications of beaches. Hubble and Cassini measurements confirm that Titan has an ocean. Titan's surface is dark brown and reddish due to organic material deposits. The Earth, where the probe landed, is filthy with water and hydrocarbons and has a consistency comparable to damp sand or clay. After analyzing Huygens and Cassini data, more evidence surfaced that Titan's lakes contain liquid methane rather than liquid water. Methane is a colorless gas that occurs on Earth in many forms, including natural gas and biogas, and is utilized as an energy source. In nature, swamps and forests can create more methane. Man-made methane is produced from rice cultivated in landfills and cattle digestive systems. Methane, along with carbon dioxide, nitrous oxide, and chlorofluorocarbons, CFCs, is a long-lived greenhouse gas that has a significant impact on the human-induced greenhouse effect on Earth. Does everything here ultimately contradict life on Titan? The disappointment was initially widespread on Earth. Many scientists believed that there may be methane-based life. However, more voices quickly emerged suggesting that this was really conceivable with our limited understanding of the universe and all of its fascinating happenings. How can we be certain that there are no species somewhere whose organisms survive on methane rather than water and can breathe pure nitrogen instead of oxygen? Opponents argue that Saturn's moon Titan lies beyond Earth's habitable zone and therefore cannot support basic life forms like bacteria or algae. The planet and its moon receive far less sunshine than we do on Earth, Venus, and Mars. However, this condition, along with Titan's extremely low average temperature of -290 degrees Fahrenheit, does not necessarily rule out the possibility of life formation. Fish and mollusks are examples of complex living forms that exist on Earth far from sunshine and heat. Complex organisms like mollusks and fish exist in the Mariana Trench, 6 miles below the water's surface, where they have never seen sunshine. Bacteria have been discovered near the poles, and a variety of mushrooms, lichens, and primitive organisms survive in cold, lonely caves. So, we must be cautious when claiming that life can only be sustained by light, heat, and oxygen. But what about Titan, which lacks its own magnetic field? Could this be why Saturn's moon may not have any life at all? No, not necessarily, say some optimistic researchers. As a result, the moon's atmosphere is almost entirely exposed to solar winds, particularly in its outer layers. However, increasing UV and cosmic radiation levels might not exclude the creation of life. Again, there are several examples on Earth where live organisms and algae survive well with severe UV levels. So, living under harsh circumstances is undoubtedly possible. Consequently, the researchers continued to search for traces of life on Titan, and they found it. After the Huygens mission, it became evident that the 32 lakes observed on Titan's surface so far are most likely filled with liquid methane rather than water. Methane becomes liquid on the Moon's surface as a result of the approximately 50% greater pressure. Space telescopes in the Cassini mission were able to uncover frozen oceans, which proved to be an exciting discovery. This is because subsequent measurements revealed that the ocean is composed of water rather than liquid methane. Researchers even assume that there is liquid water behind a thick layer of ice, with temperatures above 32 degrees Fahrenheit. If this discovery proves true, it is almost possible that this ocean of water harbors some form of life or a precursor, such as bacteria or single-celled organisms. Another probe is currently being set up to sample water on Titan. A drill would have to breach the thick layer of ice to lower a gauge into Titan's seas. Plans to develop such drills are already underway. German engineers are constructing high-performance drills in the Arctic, among other locations, to drill into the ice layers of Titan and Jupiter's icy moon, Europa, for forthcoming space missions. Titanian life is possible, according to laboratory simulations. In 2010, researchers from the University of Arizona proved in the laboratory that life on Titan is indeed conceivable. They accurately replicated the conditions in the Moon's gas shell using a combination of nitrogen, methane, and carbon monoxide that matches the makeup of Titan's atmosphere. The scientists were able to manufacture amino acids even when exposed to higher levels of radiation. The amino acids glycine and alanine are regarded as the fundamental building blocks of terrestrial proteins and, consequently, of biological life. In this experiment, both amino acids were entirely synthesized without the need for water. This proved that life is undoubtedly conceivable under Titan's conditions. During the course of an experiment, all 5 fundamental components of our DNA, cytosine, adenine, thymine, guanine, and uracil, formed under Titanian conditions. What do these discoveries prove for us? Life on Titan is possible and present. It's only a matter of time before our probes and space trips can transport more complex research facilities to moons like Titan. A probe like Huygens can only examine a limited portion of a celestial body and return data. We don't know what Titan's lakes are like or what lies beneath the supposed ice layers. It is highly possible that living entities, such as unicellular organisms, bacteria, basic fungi, and lichens, exist in caves under the surface. Furthermore, it is likely that Titan originally supported complex forms of life. The Moon has lost its atmosphere multiple times due to dramatic climate changes. This is similar to Earth's experience with the comet impact that caused the extinction of the dinosaurs. As a result, life forms on Titan might have vanished or moved underground. NASA has revealed that our next solar system destination will be Titan, the fascinating, densely biological world. The Dragonfly mission aims to unlock the secrets hidden within its icy expanses. It will undergo repeated missions to sample and examine areas surrounding Saturn's ice moon, advancing our quest for life's building components. Dragonfly will begin in 2026 and arrive in 2034. The rotorcraft will visit hundreds of prospective places on Titan in search of primitive chemical processes that are similar to those on Earth.